Have you ever stared at the ingredients on a food package or a bottle of cleaner and just your eyes glaze over? It looks like a totally different language. Well, what if I told you it is a language, a secret code, really, and by the time we're done here, you're going to know how to speak it. Let's get into it.
I mean, think about a name like sodium chloride. It sounds so scientific, so complicated, like something you'd only hear in a lab coat. But it's not just random jargon. These names are actually little puzzles, descriptions that are just waiting for us to solve them. And today, that's exactly what we're going to do.
So, where do we even begin to crack this code? Well, the very first clue is surprisingly simple. It all boils down to asking just one single question about the very first element you see in the compound's name. And here it is. This is the master key to everything. You just have to ask, does the compound start with a metal? That's it. Your answer to that one question sends you down one of two different paths, each with its own simple set of rules. If you can answer this, you are already halfway there. Seriously. And here are those two paths. If your compound starts with a metal, you've got an ionic compound on your hands. But if it starts with a non-metal, you're looking at a molecular compound. This is the big fork in the road, and pretty much every rule we're about to learn is built right on top of this one idea.
All right, let's head down that first path, the one for ionic compounds. These are the ones that start with a metal, and lucky for us, the rules for naming them are super straightforward. It's really just a three-step dance. Step 1, you just say the name of the metal. That's it. Step 2, you say the name of the non-metal that comes after it. And for the final flourish, you just chop off the end of that non-metal's name and stick iodide on there instead. Done. Let's try it out with a real one. You take sodium, that's a metal, and you add chlorine, a non-metal. So step 1, sodium. Step 2, chlorine. Step 3, change that ending, and boom, sodium chloride. You've literally been speaking chemistry every single time you've asked someone to pass the salt. Now, there's just one tiny little wrinkle for some metals. Guys like iron can have a couple of different electrical charges. So to make sure everyone's on the same page, chemists just pop a Roman numeral in the name. It's not there to make it harder, it's actually there to make things extra clear. Okay, so what about that other path? What happens when the compound starts with a non-metal? Well, for these molecular compounds, we get to use this awesome little cheat sheet made of prefixes. This little table here is basically our secret decoder ring. These prefixes literally just tell you how many of each atom you have. Di means 2, tri means 3, tetra is 4. The name is literally doing the counting for you. There is one little quirky rule you have to remember, though. Even though mono means 1, you never ever use it on the first element in the name. It's just implied. It's why we all say carbon dioxide, not monocarbon dioxide. We just kind of know there's only one carbon there. Okay, theory time is over. You've learned the rules, you've got the master key for ionic compounds, and you've got the prefix cheat sheet for molecular ones. So it's your turn to play Codebreaker. Let's see how you do. All right, first challenge, FeCl3. Okay, take a second. What's the very first question we ask? Does it start with a metal? Well, Fe is iron, so yes. That tells you exactly which rulebook you need to open. And the answer is iron 3 chloride. See, we name the metal, iron. We take the non-metal chlorine and change its ending to chloride. And because iron is one of those special cases, we use that Roman numeral 3 to be perfectly clear about which version of iron we're using. You got this. Okay, round 2. Let's flip it around. What's the formula for a compound called dinitrogen tetroxide? All the clues you need are right there in the name. Just listen to those prefixes. And there it is, N2O4. The name basically spelled it out for us, right? Dinitrogen means 2 nitrogen atoms. Tetraoxide means 4 oxygen atoms. The prefix system is so beautifully simple. Okay, so learning this is a pretty cool party trick for sure, but why does this secret language actually matter in the real world? Well, it turns out it's about a lot more than just acing a chemistry quiz. This system is, and I'm not exaggerating, the backbone of global science and safety. It makes sure the ingredients listed for your medicine are precise. It helps you understand what's in your cleaning products. It ensures scientists from all over the world are speaking the exact same language, especially when they're handling things that could be dangerous. At the end of the day, everything you've just learned is all about clarity. It means a scientist in Brazil and a pharmacist in Japan can both look at a formula like FeCl3 and know exactly what they have. There is zero room for misinterpretation, and that's what prevents accidents and keeps people safe. And that really brings us to the big idea here. Now that you're in on the secret, now that you get the logic of this language, just think about the bigger picture. In a world with so many things dividing us, how amazing is it that a simple shared system for naming things can help people collaborate and discover things on a global scale? It's a powerful idea, and now it's a language you understand.